Blackboard, you have a selection of videos that I picked to go through the various propositions in different books. Of course, this is just a small subset of what's in the Elements, but I wanted to showcase some of the variety of things that Euclid managed to prove using geometry alone, but so rich in content. Everything from geometric algebra and how to actually use algebraic operations on numbers, to circles, to the entire theory of proportions, to similar figures, which is not so far from the actual essence of geometry, but to the theory of numbers, where he actually develops things like in the book 7.1, Euclidean algorithm using purely geometric understanding of numbers as measurements. Another really fascinating thing to appear in, for example, the books on numbers is what you can find in book number 9 under the proposition 20. Let's take a look. Proposition 20. Prime numbers are more than any assigned multitude of prime numbers. Isn't this amazing? In a very geometric way, Euclid proves that there are infinitely many primes, something that every mathematical student knows to be one of the most elegant proofs in history has also originated from the Elements, but in a very different rhetoric, in a very geometry-grounded, a very particular understanding of numbers as measurements, as lengths of line segments. Now, of course, Euclid uses this approach throughout the Elements, and in our modern understanding, this sometimes results in proofs that are long-winded, and you can see here on the page, of course, an outline of the contemporary proof, something that uses algebraic notation and not Euclidean rhetoric. But you have to remember that Euclid likely used this oral tradition of passing on explanations because papyrus was, for example, of course, very expensive, and drawings on the sand didn't last very long. So he has a different approach and a different rhetorical way to pass on his justifications and explanations. However, the results are astounding in their depth of mathematical knowledge. The next thing we're going to take a look at is 3 problems of antiquity and how Euclidean geometry might not be the best way to approach it, that there might be other geometries that are more powerful, yet seemingly just as basic and just as foundational. 3 Greek problems of antiquity. If you Google it, you will easily find the 3 problems that Greek mathematicians have tried solving with straight edge and compass constructions and failed to do so. And only millennia later, these problems were proven to be impossible to construct using those 2 tools. The problems are doubling the cube. So given a cube, construct by means of straight edge and compass only a cube with double the volume. Trisecting the angle, again given only straight edge and compass. For any arbitrary angle, construct 1/3 of its measure. And finally, squaring the circle. Given a circle, construct a square with the exact same area as that of the circle. So using Euclidean constructions of straight edge and compass, we cannot accomplish these tasks, and that has been proven to be impossible. But what about other types of constructions? Maybe less classical and less restrictive, but nonetheless somewhat basic. Let's think about origami. Just like Euclidean geometry, origami has its own set of axioms, the things that we can do using folds in the paper. We can connect any 2 points with a fold that is a line. We can fold any point onto any other point, and so on. This seems more restrictive because we cannot do circles, yet we actually can solve 2 of the problems of the antiquity using origami. I strongly encourage you to pause the video and actually try these out. This is so much fun. This is what we would do in class if we were together. Get a piece of paper, follow the steps, and see if you can produce the points that will correspond to the values of doubling the cube and trisecting an angle. Here's the instructions for doubling the cube, and here are instructions for trisecting the angle. Try it for yourself. And if you need more instructions than this, next will be the video by Numberfield, who will talk through this construction and some of the justifications for the steps.
Well, Euclid had the straight edge and the compass. Those were the tools that he had available, he didn't have very good paper. A completely different approach that you can take to constructions, which is, well, it's much less classical, and so it's less talked about, is to use folding paper instead of a straight edge and a compass. Now, if you think about it, folding paper uses nothing. First of all, you can't ever do circles. You'll never be able to fold a circle onto a paper. So all you have ever is straight lines. If you think about, is this stronger or weaker than this set of tools that Euclid was using, the intuitive answer is that it must be weaker. But sometimes the intuitive answer is not the right answer. Let me just jump right in and show you how to trisect an angle by folding paper. What I'd like you to realize is that essentially you have a straight edge. Because if you have 2 points that you previously constructed somehow, then you can fold the paper so that those 2 points are on the crease. This is exactly the same thing as connecting them by a straight edge. Even better, you can do perpendicular bisector in a single step, because you can fold the paper so that these 2 points cover each other. And when you do that, the created crease will be perpendicular to the line segment connecting those points, and it will cut it exactly in half because they covered each other. So to trisect an angle, first we have to create an angle. A right angle is not very interesting. You can trisect a right angle with straight edge and compass, which is probably an important point to make. It's not that there's no angle whatsoever that you can trisect, it's that you can trisect an arbitrary angle. So 90 degrees you can trisect because you can construct a 30-degree angle. So we want to create an arbitrary angle so that our job is not so easy. So I'll just fold the paper so that the bottom of this crease is right at the corner. So this is the angle. We created it arbitrarily. We don't know how big it is. So I'll try to draw a line just inside the crease.
Okay. You're going to trisect that.
I'm going to trisect that. So first we fold the paper in half. So I just fold the bottom up to the top so that they match exactly. Then I fold the bottom up to the half. So now I have this crease at the halfway. So now I have these 2 creases, one up here and one down here. Now here's the trick. I'll mark 2 points. One is this bottom of the angle, the tip, and the second one is this point on the edge of the paper that's halfway up. I will fold the paper so that this point at the tip of the angle lines up, matches this line, this crease that I created before, and this point halfway up the paper matches this line, which is the angle itself. So I'm going to fold it and fiddle it around. Okay, now once I found that alignment, I'm going to put my hand down and crease the line. And then I take a pen and mark this point where the tip got. Okay? Open it up. And another important point to mark is where this crease that I just created with this last fold, where that intersects the bottom line. So you might already see where this is going.
Yeah.
I will fold to connect the tip of the angle with this marked point, and then fold again to connect the tip of the angle with the other marked point.
Yep.
And magic.
That's it, is it?
The angle. That's it. So since we are folding, we can check that, not prove it, but check it by folding the crease and see that it matches up. And then folding this crease in can see that it matches up. So the 3. So if you want to prove that, it's an exercise. It's doable if you remember your congruent triangles.
What power does origami have that the straight edge and compass didn't have?
Exactly. Very good question. So the trick was this one step that I did, which was taking these 2 points and lining them up with 2 lines. So if you allow that step, which is a reasonable step, I mean, if I have a paper, it's very easy to do. So the key is that if you translate this step to what it does to coordinates, the same way that I told you about in the context of straight edge and compass, what it does is this crease that it creates is a shared tangent of 2 parabolas. And to solve that equation, to find the shared tangent of 2 parabolas, you need to do something cubic.
So that was the one thing that was beyond Euclid.
That was the one thing that's beyond Euclid. And it turns out that with origami, phrased in terms of what are the constructible numbers, what are all the coordinates that we can construct, we can do addition, subtraction, multiplication, fractions, square roots, and cube roots.
So origami is more powerful than Euclidean geometry.
It's more powerful than Euclidean geometry.
Now, while the visual justification that you've seen in the video is good enough to prove that we're not way off, we of course would like an actual proof that the resulting construction will give us the trisection of this arbitrary angle. So let's see what we can do. We start with a square, as we did with the origami instructions. We start with an arbitrary angle, so whatever measure this is. We fold the 2 parallel lines here, and then we make this one odd fold where we match the 2 points to the 2 points on the other side, creating this very important crease. Okay? And we're going to use everything we have in this picture now to our advantage. So let's fill it in with the lines that correspond to this mapping of the 2 points that have created the crease and the 2 resulting angles that we have actually, the 2 resulting lines that have actually made up our trisection of the angle. Okay, so our claim here, of course, is that now these 3 angles are in fact equal. If we're going to do that, let's maybe label them with some names. So let's call them alpha, beta, and gamma. So my big claim is that alpha is equal to beta and is equal to gamma. Now, if we're going to use triangles and the resulting intersections of lines and whatnot to prove something about angles, we probably want to introduce some labels. So let's start by labeling, for example, our entire square to be something, let's say A, B, C, D. And let's label the important points that we can already see occurring within the triangles. Let's maybe call this E, say, and this can be G. And I'm going to label the 2 points that were mapped through our very important crease by E prime and B prime to highlight their relationship to E and B respectively. So these are not just some points, they are mirror images of the corresponding brothers and sisters on the other side in this very important crease line. Okay, so now I have a whole bunch of triangles that I can justify various conclusions from. I'm going to make one more line here to finish off my mirror symmetries. And that is, I'm going to create the triangle E, B prime, B. So I'm going to draw in this one particular line so that I have yet another triangle that I can use. And my very first claim is going to be that this newly drawn triangle E, B prime, B is in fact isosceles. So triangle E, B prime, B is isosceles. To see this, notice that, well, let's take a look at this triangle a little bit closer. So what I do know, for example, simply by construction, is that this line is perpendicular to this line, of course, because that's how I folded them. And I also know that I folded this particular fold by splitting this segment in half. So this is equal to this length. And of course, because the triangle, the two right angle triangles here share the side, the two corresponding triangles are equal, which makes for one large isosceles triangle, right? So this is isosceles, and I can say that because what I have is EG is perpendicular to, or rather, let's say EB is perpendicular to GB prime, and the fact that EG is in fact equal to GB. Now next, we're going to use this sort of mirror symmetry to transfer this isosceles property to yet another triangle. So what I'm going to notice is that this triangle EB prime B, when reflected in this crease line, will produce the triangle E prime B B prime, right? These two triangles are reflections of each other in this crease line. So if one of them is isosceles, then the other one will be isosceles also. So I can say, therefore, the triangle E prime B is also isosceles. Now, it looks like all I'm doing is thinking about triangles, and I'm barely thinking about the angles that I actually need to focus on. Well, this triangle E prime B actually does have two of the angles I'm interested in. So let's see what we can reason out next. If I am to concentrate on these angles, maybe I need to think about this height that was dropped from B. If the triangle E prime B is in fact isosceles, then this height that corresponds to the height GB prime in its reflection body over here will in fact divide this side into two and divide the corresponding angle in half. So simply from here, I can see that alpha is equal to beta, which is of course half of the claim to the trisection of the angle. That is fantastic news. And here we go. Next, I would like to somehow involve this angle gamma, but it might take me a little bit of the ways to get there. First, again, I'm going to use the mirror symmetry to my advantage to notice that, for example, this angle alpha is in fact equal to this angle that I don't have a name for yet, right? In my reflection, in my crease, this angle matches up to this angle. So their measures will be the same. Let's call this angle something. Let's call it theta, right? So I can see that by mirror image, alpha is equal to theta. I can also see that by the same logic, this angle beta, which is equal to alpha, we've already proven that much, is equal to its reflection partner over here, which we also don't have a name for yet. So let's call this guy, for example, delta. Right? So by simply mirror symmetry, I have that alpha is equal to this theta, which in turn is equal to beta, which in turn is equal to gamma, and whatnot. So by mirror symmetry, I can see that alpha through the chain of equalities is equal to gamma. Well, okay, you see, how does that help? But we are, in fact, almost there. One thing that we have not used yet are parallel lines that are abundant in this picture. And in particular, this line, GB prime, is parallel to BC. And this other line, BB prime, falls upon it, creating equal alternating angles. So from here, I can see that my delta is in fact equal to gamma. But delta is also equal to alpha, which means that alpha is now equal to gamma, and we have proven the other half of our claim. So, since GB prime is parallel to BC, we have that delta is equal to gamma. And combining these two expressions together, and remembering that we've already managed to prove that alpha is equal to beta, overall we have that alpha is equal to beta, which is equal to gamma, which is equal to delta, which is equal to gamma, which is what we're actually after. And that concludes my proof here. You see how origami in its folds creates so much symmetry in the picture that you can go through a variety of different arguments to get at the quality of all kinds of angles. But you still have to recall some properties of not only triangles, but also variety of interactions between lines, parallel, perpendicular, isosceles triangles. Origami is very rich in structure, and we can use this structure with the help of Euclidean geometry to prove the types of things that we can in fact construct with origami.